So, welcome to the lecture 4 of module 8. So, in the last 3 lectures on fault simulation, so what we have basically seen that that when we want to go for automatic test pattern generation, that is for a given fault, you want to find out which pattern detects it. So, we have found out that there are 2 schemes basically. So, one is based on random test pattern generation and one is based on sensitize, propagate and justify approach. So, what we have done in random pattern generation based approach? So, in random test pattern generation based approach, what we have done? So, we have taken basically a fault, basically a random pattern, and then we have found out that which are the faults that can be detected by the random pattern. So, that can we have seen 4 algorithms for that: serial, parallel, deductive and concurrent. And then the idea was that we can easily go up to say around 90% of the faults say which are easy to test. So, for the 90% of the faults, you will find out that for a new random pattern, the number of new faults that is detectable will be around say 90% of the faults can be detected by the random pattern generation. Okay, but after the 90%, there are some faults which are actually called difficult to test faults. So, they are difficult faults, and for that your random patterns cannot detect it. That is, I mean, if you apply a random pattern after say 90% of your fault coverage, you may find out that it does not detect a new pattern, or it may detect a very less number of new patterns, and then the next pattern, random pattern you apply may not detect any other fault, and this can go on. So, at that time we stop the random test pattern generation and go for sensitize, propagate and justify approach. Okay, that is this part of the curve. And that is, now we have seen that for whatever be the complexity of the random test pattern generation, let us call it say complexity of say q. Okay, then you have to multiply in the first iteration, you have to consider all the faults. Okay, so let us say that we had some n number of faults. Now again the complexity is q, and say it has detected k number of faults in the first iteration, then you can say that next the complexity is n minus k. In the following iteration, it is n minus say 2k. So, in next iteration also say 2k faults are there. We have to dot and say in the end 10 faults remain which are difficult to test and cannot be detected by random patterns. Now, you see these 10 faults were considered here, these 10 faults were considered here, these 10 faults were considered here, dot. So, for all the iterations, the difficult to test faults were considered for random test pattern generation, and the problem that happened was that could not be detected. So, in the first go say around there were n patterns, so n faults, so there were 100 faults, say n equal to 100. Then in the first pattern you apply and you verify for 100 faults. They say 20 patterns, 20 faults say get detected. Then the next iteration you go for 80, and but the major, that is after every iteration some of the faults are dropped. So, they are easy to test faults and they are adding advantages to your random test pattern generation algorithm. But you see some of the faults remain, like difficult to test faults remain, and these faults keep on lingering in all the iterations of your random test pattern generation. So, we have thought that if we can find out some algorithm or some heuristic which can say that these are easy to test fault and they are difficult to test fault. So, what we will do that these difficult to test faults will not at all bring it into the paradigm for random test pattern generation. We will try with only the easy to test faults, and difficult to test faults we can keep in a separate bin and go directly for sensitize, propagate and justify approach. So, what this will help? This will actually help in optimizing the random test pattern generation algorithm, because we will be not trying in every iteration the faults which linger that are difficult to test for. Now, let us see how can we find out some kind of algorithm or a heuristic that can tell you which is the easy fault and which is the difficult fault. So, let us start with an example. So, this is a simple circuit. So, let us consider that okay, let me just tell you some formal notations we will be using. So, when we say that CC0, that is actually called combinational controllability of 0, okay. And if you say CC1, then we say that is combinational controllability of 1, and we also put a line L, that is a net L. So, if we say that CC0 of OG3, so what does it mean? It will mean that how difficult it is to get this line to get the value 0, combinational controllability of 0 for this output. The name of this output is this one. So, if we say that CC1, so if we say that CC1 OG3, that means how difficult is to make this line to 1 and this net. So, these are the 2 notations we are generally going to use, and then we will add one more that we will tell you later. So, let us consider this circuit. Now, say at this net, say we are considering a stuck at 0 fault and a stuck at 1 fault. Now, we just try to find out which is the easy fault to test and which is the difficult fault to test. So, let us first consider that we are going for the stuck at 0 fault. So, if you are allowing a stuck at 0 fault, then you have to apply a 1 over here, right. So, that is what is there, and then also we have to apply a 1 over here. Then you can observe the value here, correct. So, this is your so if this line is stuck at 0, so you will get the answer 1 0, this is 1 and the answer is 1 0 and you can detect it. So, in fact, you have to apply a 1 here and you have to apply a 1 here. Now, so you can say that the difficulty of getting this stack at 0 fault here is combinational controllability of 1 you have to get at OG3, this you have to tell that you have to make this line 1 and this line also you have to make it to 1. So, it is combinational controllability of OG4 because of this gate and you have to control it to 1. So, if you add this two, that is you have to control this to 1, that is combinational controllability of OG3 plus combinational controllability of OG4, this one. If you add it, then actually you can get the value of what is the difficulty of testing this one. So, let us see, just try to give some estimate. Okay, so, in this case you have to get a 1. So, what are the possible inputs here? 0 0 0 1 1 0 1 1. Okay. So, how difficult is to make it to 1? It is, you can add a number that the difficulty in controlling this one is say 1 by 4, because only one, because among these 4 patterns you can apply only one of them will succeed in making this one as a 1. So, you can say that because 1 1 is required to test it, make it a 1. So, you say that 1 1 and so you can say that combinational controllability of 1 to OG3 is actually 1/4, because only one of the 4 combinations can do this one. Now, in this case you have to apply a 1 over here. So, you see 1 2 3 4 lines are there. So, 16 possible combinations are there and when you can get a 1 you can get 1 2 3 4. So, only 1 by 16th of a pattern can get you a 1 over here. Okay. So, you can say that it is 1 by 16 plus the order of difficulty is 1 by 4, something like this, correct. So, now you can say that for a stuck at 0 fault here. So, for a stuck at 0 fault here, you remember that these are combinational complexity 1 by 16 plus 1 by 4. Now, let us try to do the same thing for the stuck at 1 fault kind of a thing in the same net. Okay. So, in the same net we are going to do that. Okay. So, same net we are now going to take a stuck at 1 fault. So, stuck at 1 fault means you have to apply a 0 over here, obviously this is controllability. So, this is you have to apply a 1 at this net. Okay, and this is a stuck at 1. So, the answer is 1/0 and the 1/0. So, now how difficult is to take a stuck at 1 fault here? It is 1 by 4, because this line has to be made a 1 which is similar, plus you have to make this net 0. So, again these 4 inputs are there. So, there is 16 combination and 15 out of them, that is 0 0 0 0 to 0 1 1 1. Actually, accepting 1 1 1, 1 1 1 1 will give is a 1, we want a 0. Accepting this combination, all other 15 combinations can give a 0 over here. So, you can say that the difficulty of controlling or how you can get the value is 15 by 16 and 1 by 4. So, this 1 by 4 is common to both the stuck at 0 fault here and stuck at 1 fault. So, let us eliminate this. So, you can say that combinational controllability of OG4 to 0 is 15 by this one, and combinational controllability of difficulty here is 1 by 16. So, now you can see what happens is that to test a stuck at, because this 1 by 4th here, this one get value 1, this net is same for all. So, let us forget about it. Now, a stuck at 0 fault here needs the application of a 1. So, whose probability is 1 by 16. Now, to apply a there is 1 by 16. Now, to test a stuck at 1 fault over here, this probability is 15 by 16, that is 15 combinations out of 16 which. So, obviously, testing a stuck at 1 fault here is easier than testing a stuck at 0 fault here. So, if I were to apply a random test pattern generation, then I could have said that you take this stuck at 1 for a random test pattern generation, it is easier, because 15 out of 16 combinations can help you, that is and 1/4, that is and 1/4. So, this is common for all. So, out of 15 combinations can help you to detect the stuck at fault, and only 1 out of 16 combination can help to detect a stuck at 0 fault, which is a very difficult problem. So, better for the stuck at 0 fault you go for a what you call a sensitize, propagate and justify approach, and for the other you go for this stuck at 0 fault you go for a for the for the stuck at 1 fault you go for a random test pattern generation. So, the stuck at 0 fault at O4 is more difficult than a stuck at 1 fault at this one. So, by this algorithm kind of a thing, you can easily find out that which is a easier to test fault and which is difficult to test fault. So, this is a basic notion which is actually, I will tell you what you mean by SQUAP and all. So, this is a basic notion that how can you determine that which is a, or you can say that how to determine which is a easy to test fault and which is a difficult to test fault. So, here we have found out a procedure, but you also have to observe that at the same time we have also generated the test pattern. That is what we have done. We have said that you have to apply a 1 over here. So, 1 and 1 is the test pattern, and here to test a stack at 0 fault you have to apply 1 1 1 1, only one combination, and here you have to apply any, and for the stack at 1 fault here any other combination other than this one. So, indirectly what we have done, indirectly we have generated test patterns for finding out which is the difficult to test fault and which is the test fault. So, this is not a very good approach. So, what we have said that for the stack at 0 fault the test pattern is this one, say one pattern, because all ones, because we have said that for to test a stack at 1 fault, let us take this case, that why we are saying that to find out which is easier or which is difficult to test fault we are applying all the patterns. Say for the stack at 1 fault you have to apply a, sorry, for the stack at 0 fault we have to apply a 1 over here. Okay, so, the answer is 1 1 1 1. Okay, and for this one also has to be 1 value to be propagated. So, you have to 1 1. So, we have generated the test pattern by sensitize, propagate and justify approach indirectly. So, stack at 0 you apply a 1. So, this is sensitize. Now, this value has to be propagated to the output. So, you have to apply a 1 over here, and then we are saying that this is the pattern that has to be applied. And for the stack at 1 fault, so what we have done? We have said that any other pattern other than this thing will hold. So, basically what we have done, so we have gone for sensitize, propagate and justify. So, we are ranking of their faults based on difficulty of testing, but we are also generating the test pattern. So, that is not a very good thing we are doing because of the complexity. So, here we are actually saying that we are trying to find out which is the easier fault and which is a difficult set of faults. For that we are actually going for a sensitize, propagate and justify approach, which is a very complex algorithm. So, to solve a simpler problem we are taking a bigger algorithm and trying to solve it. So, that is actually not wrong, but we are, our main emphasis is that we want to find out a very simple algorithm. Maybe it is a heuristic, maybe it will give approximate results, but our main goal was to find out that which are the easier set of faults and which are the difficult to test set of faults. Now, by doing this approach which I discussed in the last slide, what we are doing? We are doing a ATPG kind of a thing, that is we are using sensitize, propagate and justify approach, and by that we are finding out which is easier fault and which is difficult to test fault. So, this does not have any meaning, because we are generating the test pattern by we have two algorithms. One is random test pattern which is easier and which is low complexity, and we have test sensitize, propagate and justify approach which involves more complexity. So, what we are doing is we are using a more complex algorithm to find out which is a easier fault and which is a difficult to test fault. Does not have any meaning, because now our idea was that we have to find out a very simple low complexity algorithm which can tell you which is a easy fault and which is a difficult fault. So, difficult faults will throw to sensitize, propagate and justify approach, and easier faults will go by what you call random pattern generation. But now this algorithm in the last slide, it actually finds out which is an easier to test fault and which is a difficult to test fault, but for that you are using an algorithm which is a very complex one, that is sensitize, propagate and justify approach, and then you are finding out which is easier and difficult. So, I may say that why you want to classify them as difficult and easy, you apply sensitize, propagate and justify approach, and then everything you get difficult faults as well as you are going to get the test patterns. So, that high complexity algorithm of sensitize, propagate and justify approach you are using to find out which is the easier fault, which is difficult, does not solve our purpose. Our purpose is that we have to use sensitize, propagate and justify algorithm as minimum as possible and only for the difficult to test fault. So, we cannot use a complexity algorithm to find out which is the easier fault and which is a difficult fault. We have to find out some easy to test faults and difficult to test faults using a very simple algorithm, or maybe, but it may give some approximate result, that is possible. Then for the easier faults we are going to use a simple algorithm, that is random test pattern generation, and for the difficult to test faults we can use the complex algorithm for sensitize, propagate and justify. So, this is the case. So, our idea of we have to find out a simpler algorithm to find out which is easier fault and test fault. So, we are going to study SQUAP, which is the algorithm which is Scandinavia Controllability Observability Analysis Program. So, it is a very simple algorithm, as we will see. It does not require to go for sensitize, propagate and justify. What only it will do, it will scan the circuit and it will approximately tell you which is easier to test fault and which is difficult to test fault, but it may be approximate and give you approximate result. But it can give you a clear idea that which are easier and try to do it random, and which are difficult then go for sensitize, propagate and justify. So, now we will study this algorithm in details. So, before that we see some notations. So, CC0FL already we told you, it is controllability of 0 at net L, and how difficult is to control the net L to 0. CC1 is how difficult is to control the net at 1, and there is one more, that is combinational observability of L, that is say for example, this is a net L and there is lot of other circuits and this is the output, primary output. Then CC of O, that is CO of OL, that is the combinational observability of L, that is how difficult is to observe this line at the primary output. So, to test a circuit, say if it is stuck at 0 fault, say, then you have to apply a 1 over here. So, we have to find that combinational controllability of 1 at L, okay, because if you apply a 1 then stack at 0 fault can be tested, as well as this L value has to be observed at the primary output, that is CO of L. So, you have to add CC1L plus CO of L to get take a stack at 0 fault. Now, if you want to have test for stack at 1 fault, what you have to do? So, if you apply 1 to stack at 1 fault, then you have to apply a combinational comparative of 0 at L. If you stack at 1 fault here, you have to apply a 0. Now, this effect has to be propagated to the output, that you have to observe the value at the output. So, it is combinational observability of L at primary output. If you add them, then you get the difficulty of how difficult it is to take a test a stack at 1 fault at the net L. Okay. So, now sometimes we use a short notation like say N1, N2 and N3. So, N3 for a net L. So, we say that N1 stands for CCO of L, N2 stands for CC1 of L and CO stands for combination observability at net L. This is some short notation which we sometimes use. Now, we discuss the SCOAP procedure. So, what is the SCOAP procedure? The SCOAP procedure is first all primary inputs are assigned 0, CC0 and CC1. So, what is the idea? So, all the primary inputs we assume that it can be easily controllable. So, the difficulty of controllability of CC0, that is making a primary input 0 or primary input are 1, that is the assumption. That is assume that the primary signal is directly controllable and their observability effort is proportional to 1. That is, if you have an AND gate, say these are all the primary inputs, then CC0 is of this input is 1 and also for this one is 1 and controllability of 1 is also for this nets are 1. That is, primary inputs can be directly controllable and difficulty level is 1. Then what we do, CC1 and CC0 are determined level wise using some logic rules. So, in the last lecture we have seen that for the deductive fault simulation there are some rules, that is from one level to another level in the circuit if you go you have some rules. So, now here we will also study some of this what you call these combinational circuit rules we will also study, that is SCOAP rules, that if you go for one level of the circuit to another level of the circuit how the rules are applied. That is, if you know that CC0 of this net and CC0 of this net, then what is the value of CC0 of this? If you know CC1 and CC1 of this, then what is the value of CC1 of this net? Okay, so that is that level propagation, how difficult it is to control and how difficult it is to observe. So, all those things we will study, that is the rules. So, now primary inputs you apply CC of 0 and CC of 1 as 1 1, that is difficult to control the primary inputs are 1 1, that is fine. Then you go for the next level of the gates, then you have to apply some rules that we will study in a similar way. So, you have to go to the similar rule, if you apply then we can go from the primary inputs to the primary outputs, every net will have the value of CC0 and CC1. Similarly, we have to go for combinational observability. Combinational controllability goes from primary inputs to primary outputs, this is the level of propagation. But for the combination observability CO we go for the reverse way. So, we assume that the primary output lines are very easy to observe, directly if you probe and you can observe. So, difficulty level is 0. So, primary input controllability difficulty is 1 and primary output observability is 0. So, you may ask the question that primary outputs are directly available as the output. So, why you make it as 1, and similarly the controllability, similarly the primary what is the question is that the primary input controllability is 1 1, that is the first statement, but the observability of the primary output is 0. So, you may ask the question that why it is like that, that primary input is directly controllable, so you are giving a 1 and the primary output directly observable, but you are not giving a value of 1, you are saying that it is 0, why is it possible? So, now here the assumption is a heuristic, is not an what you call exact algorithm. So, the assumption it is there that to control a line you have to put some effort at least. So, they are saying that the primary input controllability are 1. Okay, but the observation is more simpler, just you probe it and you get the value. So, they say that observability difficulty is 1 less, that is 0, that is just a heuristic. You can also try out with controllability value of 1 1 at the primary inputs and observability at the primary outputs as also 1. You can try out and find out that you may get another version of SCOAP, but the analysis is not different, that is whatever SCOAP with primary input controllability of 0 0 and output observability is, primary output observability is 0, the value of the cluster of easy to test faults and difficult to test fault you will get will be very similar if you apply the logic that controllability of primary inputs is 1 and also observability of primary outputs is 1. So, there is not much difference in the results because they are heuristic algorithms, and so therefore, we go by the what is the proposed by the literature, that is difficulty to control the inputs is 1 and observation is more easier. So, primary output observability is a 0. Following that, we know that the primary output controllability values of all the primary outputs are 0. So, now it is 0 basically. Now, you have to come out from this level to this level and you have to apply some rules and then you can find out the controllability observability of all the nets, but you have to traverse the circuit in the reverse direction. So, once you have traversed the circuit in two directions, this direction we start with combinational controllability of 0 of primary nets equal to 1, and then we apply rules and at every net you get CC 0 and CC 1. So, here also CC 1 of the primary inputs are all 1s, and finally, for the primary output you get all the values of CC 0 and CC 1. You go by this way. And when you are going for the observability part of view, the primary output observabilities are, we say that primary output combinational observability of the primary output equal to 0, and there are some rules, you keep on applying them and then you get the value of primary observability of all the nets in the circuit from primary output to the primary inputs. So, now as already discussed, so given a net difficult to test a stack at 0 fault is, you have to control the net to 1 and you have to observe the value of the output. So, it is CC 1 of L plus CO of L. Similarly, when stack at 1 fault means you have to apply a 0. So, difficulty to make that net to 0 and you have to observe the net at the output. So, this is how we can find out the difficulty to test a stack at 1 fault and stack at 0 fault. Now, we will study about what do you call these rules, because we said that with primary inputs controllability we know that they are equal to 1, observability primary output is 0. But now how to propagate? So, for that we require some rules. So, let us see of an AND gate with 2 input out as this one and this one. So, now say for example, these are the rules, see the rules later. So, now see how difficult is to control this C value to 0. Okay. So, C value can be 0 when this is 0 or this is 0. If either of them is 0, so we know that this value is 0. So, how difficult is to make this C to 0? So, it is minimum of combinational controllability of 0 of A or combinational controllability of B to 0, plus you have to add a 1, that is because of the level shift, this is from this level to this level. So, difficulty is increasing we assume and we add a 1, but to make a C 0, how difficult it is? It is if it is to make C 0, we have to apply either A 0 or B 0. So, if A to 0 is easier, then we say that we will apply A 0 and we forget about B and the answer is 0. If B is easier to apply to 0, then we will apply B 0 and forget about A and then automatically C will be 0. So, minimum of the difficulty of making A 0 comma B 0 is the difficulty of controlling C to 0. That is whichever is easy, A is easy or B is easy to make 0, that we will take and we will add 1. That is why we say that minimum of combinational controllability of A and combinational controllability of B. That is easier to make A as 0 or B as 0 is the equivalent to combinational controllability of C to 0 and you have to add a 1 because there is a level shift. Now, let us see what is the difficulty of making C as 1. Making C as 1 is a more difficult problem because A has to be 1 as well as B has to be 1. There is no choice or something. So, it is how difficult is to make A as 1, this value, how difficult is to make B as 1, those values you have to add, because together you can make C equal to 1 and then you have to add a 1 because there is a level shift. So, this is the rule for CC of 0 of a AND gate and CC of 1 of a AND gate, provided that we know the value of CC 0 of A, CC 1 of A, CC 0 of B, CC 1 of B. That is what is written. To control the value of C to 0, either A to be 0 or B to be 0. So, CC 0 is the minimum difficulty to control A to 0 or B to 0. We add 1 as we propagate the level. So, CC 0 is this one. Similarly, for CC 1 you have to add them because both of the A and B has to be 1 and there is a 1 for a level shift. So, these are the two rules you have to remember for a AND gate. Now, we will see for a NAND gate. So, how can we get a NAND gate to be 0? So, NAND gate is 0 if we have 1 and a 1 over here. So, difficult to make C as 0 for the NAND gate we are looking at. So, it is CC 1 of A, you have to make this one to 1 as well as you have to also make this one to 1. So, both the controllability difficulty you have to add plus 1 there is a level shift. Now, so this is the value of CC 0. Now, if you have to make C equal to 1, then anything, this is 0 or this is 0, any of them is 0 directly makes this one as 1. So, it is how minimum of this difficulty plus you have to add a 1. So, this makes your rules for the NAND gate. So, you have to remember these rules. Now, you go for an OR gate. So, OR gate is always the dual of a AND gate. So, let us see. So, if you want to get a 0 over here, so you have to apply a 0 and a 0 over here because any other combination make a 1. So, the combinational difficulty of 0 at this plus combinational difficulty of 0 at B plus 1 is the level shift because both of them has to be 0 and 0. So, this is the value of CC 0 at this one. Now, to make CC equal to 1, then there is either this one is 1 or this one is 1. Any of them is 1 will get you this one. So, it is minimum of the difficulty of this one to be 1 and or difficulty of this one. You have to take the minimum of them and you have to add a 1 for level shift. So, CC 1 of this one is minimum of difficulty to make A as 1 comma difficulty to be an so minimum of them you have to take and 1 you have to add for the level shift. So, this is the rules for a OR gate. Similarly, we can go for the NOR gate. So, NOR gate whenever you get a 1, you get a 1 whenever you have a 0 and a 0. So, this is the value and whenever you get a 0. So, it is either this one as a 1 or this one as a 1. So, this is your rule. So, this is a very simple rule, now you can easily understand, and 1 is for the level shift. So, this for the NOR gate you have to remember. Now, you see in the interesting case is for a XOR gate, that will require some fine time for explanation. So, now what was there? So, in case of the XOR gate, what you see that say 0, we want to get a 0 over here. So, what are the possibilities? So, to get a 0 over here, so we can apply a 0 0 over here or a 1 1 over. Any of these two combinations will apply a 0 over here, correct? So, now what is the idea? Any of them will have a 0. So, either if this is easier to apply, then we will get this one. If this is easier to apply, then we will apply this one. So, either of these two which is easier to do will apply and we will get a 0 over here. But now, there is a size difference between the OR gate in case of AND gate and OR gate. So, what is the idea? So, if you want to get a 0 over here, so either you apply a 0 over here or you apply a 0 over here. Either of them which is easier can be used to control this to 0, but there is either this or this, any one of them. But in case of an XOR gate, one pattern, that is input pattern at one input, is not going to suffice. You have to consider the input at both the patterns, and then only you can say that which one is easier to test and which one is difficult to apply. So, that is in case of AND gate, only one input, this difficulty of this level and difficulty of this level, if you OR it or you add it, you are going to get the answer for combinational controllability 0 and 1 at this output. But for the XOR gate, it is somewhat different. So, one input, you cannot use one input to get a 0 or a 1 directly. For an AND gate or a OR gate, so one input if you control, you can easily get a 0 and a 1 at the output by controlling. For 1, actually for AND gate you have to apply 1 1, but for a 0 you have to apply a 0, then any of the inputs if you apply a 0 you can get the output. But for the XOR gate to apply a 0 or a 1, so never you can say that that is one input can control this value. So, for XOR gate to get the value of 0 and 1 at the output, both the input values you have to know. This is unlike AND gate where 1 gate 0 implies that this is a 0, OR gate 1 is a 1, this even if you do not know, you know that the answer is a 1. So, this does not hold for an OR gate, that is why the controllability and observability for the XOR gate is a bit different. So, to get a 0 over here, either of these will apply. So, we say that CC 0 of A, CC 0 of B, that is difficulty of applying a 0 0. CC 1 of A and CC 1 of B, that is difficult to apply a 1 1. So, minimum of these two. So, whichever pair is easier to apply, that minimum you have to take, that is actually can give you a 0 over here plus you add a 1. So, this is the controllability of XOR gate to 0. Now, if you want to apply a 1 at the output, how difficult is it? So, there are again two patterns 1 0 and 0 1, then you get the answer as 1. So, how difficult is to apply the pattern? CC 0, sorry, how difficult is to apply this pattern? Not this one. See, this CC 0 of A and CC 1 of B. How difficult is to apply the pattern 1 0? This is CC 1 of A and CC 0. So, easier of these two you will apply, plus a 1 you have to go for a level shift. So, these two formulas will give you what is the what you call it will give you what is the difficulty of CC 0 and CC 1 of XOR gate. So, XOR gate is a bit difficult to do this. Now, for the inverter, it is very simple, you get a 0 over here, you get a 1 over here. So, to get a 1 over here, what you have to do? Difficult to apply a 0 over here plus level shift. Now, if you want to get a 1 over here, sorry, a 0 over here, you have to apply a 1 over here. So, CC 0 of this one is you have to apply a 1, difficult to apply this one and a level shift. So, inverters are very simple, you want to get a 0, apply a 1, how difficult to apply a 1 that you find out, add a 1 because of level shift, you are done. Similarly, for this case. So, inverters is the very simple one and XOR gate, as you can think, is the most complex one to think about these things. Now, for a fan out. So, say for example, you know that CC 0 of A we know and CC 0 sorry 1 of A also you know. Then if you control this to 1 0, then automatically all these things will be 0. If you make this one to 1, then automatically everything will be 1. So, if the difficulty of this net to be controlled to 0 is CC 0 of A, so obviously the difficulty in controlling this one to 0, sorry, we are starting with the 0. So, if we know that CC0 of A is some value we know, then this 0 is applied and all the nets will be 0. So, if you apply a 0, automatically everything will be 0. So, if we know the difficulty of controlling CC of 0 to CC of A to 0, then automatically same value will apply for C1 of 0, CC0 of C2, CC0 of C. Everything will be same, because if you just apply 0, automatically it is carried over, and there is no level shift because there is no gate, so you need not add a 1. Similarly, if you apply a 1 over here, then we say that CC of 1 of A we know, this difficulty you know. So, immediately apply a 1, 1, 1, 1, 1 will go here. So, CC of 1 of C1 is equal to CC of 1 of A, same value, because how difficult is to make A as 1, the same value of same amount of difficulty will be used to apply a 1 over here, 1 over here, 1. Because you are directly applying this 1, you are directly getting the value of n. There is no gate inter between, so we need not add 1. So, 1 is not required to be added, this 1 is never required to be added at the next level. So, directly you can say that for the fan outs. So, whatever is the difficulty of CC0 over here, the same thing will be applied, CC1, the same value will be applied here, because there is no level shift and nothing is there. So, still now we have seen the rules to control a line, and also that is to control a line from 0 to 1, and so till now we have seen how difficult is to control a line to 0 and how difficult is to make control a line to 1, that is the level rules. That is, if you are giving an AND gate, if you know the controllability values of the inputs, how to calculate the output, OR gate, NAND gate, NOR gate, XOR gate, all the values we have found out. If you know the CC0 and CC1 of the inputs, you can easily compute the value of CC0 and CC1 at the output. Similarly, we have seen for the for the fan outs. Now, we will see similar rules for CO, that is, if you know that the observability is the primary output, how do you know that, how to control, how do you know the values of the primary input, that is reverse propagation, right. So, now let us see this case. Say for example, we get that CC0, the primary output may be whatever. So, we know that combinatorial compatibility of C, this value we know. If the primary output is 0, but say we know that it will be a non-primary input also for the time being. So, let us see that we know this value. So, now, say you know that difficulty of observing this line is this one. Okay. Now, you find out, now you need to find out how difficult is to observe this line at the primary input. So, you see, so we know that to traverse the fault effect from this one to this one, we need to apply a 1 at B, correct. So, if you apply a 1 at B, so we know that this value can be forwarded to the output, correct. So, now what is say that? So, to observe this A, so what we need to do? First we need to make B 1. So, we know that combinational controllability of 1 to B, that has to be done. Then actually this has to be observed. So, if you apply a 1, then A will be reflected at C, correct. So, now but how difficult is to observe C, because A is now reflected from here to here by applying a 1 over here. So, we say that difficulty of combination observability of A is equal to, you have to make this B as 1. But by making B as 1, A is now only propagated to C, it is not propagated yet to primary output. So, how difficult is to move it to a primary output? That we know is that is equal to combinational observability of C, because combinational observability of C will tell you how difficult it is to observe C at the primary output. So, we say that combinational observability of A is equal to combinational controllability of B to 1, you make B as 1, value of A is reflected at C, and we know that how difficult is to compute the value of C, observe the value of C the primary output, we know that is C of 0 C. This one plus 1 you have to add, because there is a level shift. So, that is the value, combination observability of A is equal to combinational controllability B to 1, observability of C plus 1 is a level shift. That is what is actually said in the line what I have explained. It is said that to observe the value of A at a primary output, B is to be 1. So, CO of A is difficult to control B to 1 plus observability of C, because you are observing A through C. So, we add 1 to CO as we are progressing by a level from output to input, and so we have to add this controllability of B, observability of C, because you are observing A through C, and 1 for a level shift. And now we get the formula. Similarly, if you want to observe B, so what you have to do? You have to make A as 1. So, combinational controllability of A as 1 plus you have to observe C, because B will be again observed as C. So, this is there, and 1 for a level shift. So, these are the rules for a observability of a AND gate. Now, if you let us look at the observability conditions for a NAND gate. Okay. So, NAND gate, say for example, if you want to observe this A, then what you have to do? If you have to observe this as A, we know that we have to apply a 1, because if you apply a 0 over here, obviously it is non controllable and everything will be, if you apply a 0, everything will be 1, and your whole purpose of test pattern generation is lost. So, you have to apply a 1. So, it is combinational controllability of B to 1, A is observed via C. So, this is there and 1 for the level shift. Similarly, for B it is A has to be made 1. So, combinational controllability of A to 1 plus you have to observe B via C. So, this is the case and 1 is added for the level shift. So, these are your rules for observing A and B for a AND gate. For the OR gate, we always know that it is a dual of AND gate. So, let us see that if you want to observe A, then obviously B has to be made 0. If B is 1, then C will become 1 and the whole purpose of test pattern is lost. So, combinational controllability of B to 1, you have to B to 0 you have to find out, this is the case. And then CCO of 0, combinational observability of C you have to take, because A is observed via C. So, that you have to add and plus 1 for the level shift. Similarly, if you want to observe B, then what you have to do? You want to observe B, the output, then A has to be made 0. So, this is the case. 1 for the level shift you have to do, and you have to observe C. We have to know the value of observability of C, that is B is observed via C. So, combinational controllability observability of B is difficulty to observe C plus difficulty to make A as 0 plus 1 for a level shift. Similarly, for a NOR gate also you can find out in the same way that these are the rules. I am not going into details. So, these are the rules for the NOR gate. Now, we have to again observe carefully for the XOR gate, because XOR gate is the most complex one. So, let us see how it can be done. Say for example, you have to observe this at this output. So, now we all know that if B is equal to 1, then what is the value of C? C is equal to A bar, because we know that XOR gate is a controlled inverter. If you apply one bit as a 1, then value of you get as a inversion. So, if you like, say if you apply a 1 over here and let A be 0. So, 0 and a 1 will get the value of a 1 over inverse, so the X prime, so A prime. So, now if A is 1, then 1 and a 1 you get a 0 at the output C, that is again equal to A prime. So, if you apply 1 bit, so that is why we called what you called XOR gate is a controlled inverter, because if the one input is 1, then the other input actually gets inverted. Similarly, if you apply a 0 over here, then C will be equal to A. So, that is the idea. So, either you get A or you get A prime, depending on whether you apply a 0 over a 1. So, see, now both of them serve our purpose, because our goal is that we have to observe A, we can propagate it here. So, we can observe A also, we can observe A prime also, both of them solves our purpose. Like this may be says normal case 0, fault case 1, and this may lead to normal case 1 and fault case 0. And both of them will lead to our fault detection. So, propagation of A or A prime, both of them, this suffices our purpose. So, how difficult is to observe A? So, B is either 0 or 1, anything is possible. So, it is minimum of difficult to control, minimum difficulty of controlling B to 0 or B to 1. So, if it is easier to make B equal to 0, you take B, then you get C equal to A. If it is more easier to get B equal to 1, then you will get A prime, fine, then you apply 1. The choice is yours, whichever is easier you apply, either you will get C equal to A or A prime. So, minimum of this one 0 or 1, whichever is easier to control, then you apply, plus again A will be observable via C. So, that is control observability of C is to be there, and 1 for a level jump. So, this is how it is somewhat bit tricky for the XOR gate compared to the other gates, observability and control both. Now, if you say want to observe B at the output. So, similarly, if A is 1, then you get B prime. If A is equal to 0, then you get B. Okay. So, both of them is okay for us. So, if A is easier to make to 1, you apply that. If A is easier to be get to 0, you do that. So, minimum of controllability of A to 0 and A to. Okay. So, whatever may be the case, you do that. Okay. So, there is a slight mistake in this figure, I will just tell you. So, what it is written correctly over here. So, to control A to 0, it is minimum of CC 0 of B and CC this as 1. So, this is actually this is proper, but in this case to control B, this has to be an A. No, this is correct. So, this is a small typo over here, just note it. So, this will be actually this one. Okay. Why? Because if you want to propagate B, so if A is easier to control, make A equal to 0. If 1 is easier to get at A, make CC 1 of A. So, this is the case, and 1 for the level jump, and it is observable via C. So, make this one and this one. So, there is a slight mistake. So, this one will also be A, correct. So, this is how we go for the computation for a XOR gate. Now, for an inverter, inverter is the most simplest one. So, how difficult is to observe this? This one, because this one you have to observe from here. So, it is very easy if you get A equal to 0. So, you will get A equal to 1 and it can be observed. Similarly, if you want to apply 1, you will get 0 and it can be observed. So, but only thing you have to remember that this one is observed via C. So, difficulty of C is only mattering over here and this is a level jump. So, if you want to observe A, you have to observe C and plus 1 for the level jump. So, this is the case. So, there is nothing. Combination observability of A is CC of 0 plus 1 and this thing is not rule, same rule is written over there. So, I mean because for both for 0 and 1, this is you can say for 0 and 1 both the case is validated. Both the case means if A equal to 0, A equal to 1. So, both the cases the same phenomena observed. So, we have written it twice, but otherwise not required. So, you have to observe C, if you want to observe A plus 1 for the level shift. So, this is the most simplest one. Now, for the now we go for what? We go for the fan out. So, fan out is the most interesting, or you can say fan out you have to deal in details. I mean not in details, but you have to with some thought. So, you have to observe this one, say via this, via this, via this. Now, you think that there is a very big combinational cloud over here, there is a very big combinational cloud over here, but here it directly goes to the primary output. Then how difficult is to observe the line? How difficult is to observe this one? Because we want to observe this. So, this may be a very complex cloud over here, you have to observe it very difficult. Here also somewhat difficult smaller cloud, but this is directly primary output. So, wherever is the minimum difficulty, you have to take that. It is very simple. So, combination observability of A is minimum of observability of this. Whichever is minimum observability difficulty or whichever is easiest to observe among these three, that one is the case. So, what do we write? So, if you see what do we write? We write that combination observability of A is minimum of this or minimum of this. Whichever is the easiest to observe, we will take the output of A via this line. So, this is your formula. So, now till now we have seen the rules for what? So, we have seen the rules for combinational controllability of 0, 1 for all the gates. We have also seen the combinational observability rule for all the gates. Now, what we will see? Now, we will explore this for an algorithm, for a simple circuit. So, this is an example. So, let us first see for combinational controllability of 0 and combinational controllability of 1. So, the notation is 0 0 means this one is combinational controllability of 0 and this one is combinational controllability of 1. So, this is how we write it, comma. So, let us see how we are going about this. So, in this case you see we write this one as 1 1. Why? Because making this line 0 or 1, that is combinational controllability of 0, combinational controllability of a primary input is always 1. Okay, so, we write it as 1 1, that was the default. So, this is also 1 1. Now, we have seen that for a fan out, if you apply a 0 over here, everything will get 0 over here. If you apply 1, everything will be 1 1 1. So, controllability of the stem is directly reflects over the output. So, this is the stem. So, if the controllability of 1 and 0 0 and 1 are 1 1, so they directly reflect over there, because whatever value you give here directly comes. So, this is 1 and a 1. Now, so this is 1 1, this thing I have written over here and this is 1 1. So, now how difficult is to, so this is level 1. Now, you see, so this is 1 1 and this is 1 1. Now, let us will calculate for this and this level. So, how difficult is to get a 0 over here? This can be 0 or this can be 0. So, how difficult is to make this line to 0? 1. How difficult is to make this line to 0? Is 1. So, either of them if you make as this difficult, you can say combinational controllability of 0, combinational controllability, both of them are 1. Okay, both of them are 1. Now, either this is 0 or this is 0 will solve our purpose. So, minimum of 1 comma 1 is 1 plus there is a level shift. So, we get the result 2. So, that is 1 minimum of 1 comma 1, that is combinational controllability of 0 at this and combinational controllability of 0 at this, that is this one or this one. Minimum you have to take plus 1 for a level shift. So, minimum 1 1 is a 1 plus 1 is a 1, so get a 2 over here. So, combinational controllability of 0 at this net is 2. Now, if you have to, now let us see combinational controllability of this net to be 1. So, if you want to get this as 1, so what you have to do? You have to apply a 1 over here and a 1 over here. So, combinational controllability of 1 at this net is equal to 1 and combinational controllability of 1 at this net is 1. So, what is the, how can you get a 1 over here? Is combinational controllability of 1 at 1 net plus combinational controllability 1 at B net, this is A net, okay, plus 1. So, it is 1 plus 1, 2 plus 1 because the level shift, so it is at 3. So, we get what? We get a simply we get a 3 over here, that is actually combinational controllability of 1 at this one, that is 1 plus 1 plus this plus 1, right. Now, for the OR gate, so we want to do it. So, we know that 1 1 is the combinational controllability of 0 and 1 over here. So, what is the combinational controllability of this one? Simply this one plus you have to apply 1 1 for the level shift. So, combinational controllability of 0 at this one is combinational controllability of 1 here plus 1, this is 1 plus 1 is 2. So, now if you want to find out the combinational controllability of 1 here, so it is combinational controllability of 0 here plus 1, that is 1 plus 1 is 2. So, we get the value of 2 2. So, this solves for the level 2. Now, you have to compute for this one, which is also very simple. So, you know that we want to get a 0 over here. So, to get a 0 over here, you have to apply either a 0 over here, either a 0 over here. So, what is the combinational controllability of this net? So, it is combinational controllability of this net is how much? So, it is combinational controllability of this net to 0 is how much? It is 2, and combinational controllability of this net is how much? It is also 2. So, minimum of 2 and a 2 is 2 plus 1 for a level shift. So, you get a 3 over here. Okay, so, this combinational controllability of 0 at this net is 3. Now, say we want to get a 1 at this net. So, to get a 1 at this net, you have to apply combinational controllability of 1 here and a combinational controllability of 1 here. So, what is the combinational controllability of 1 at this net? It is 3. Combinational controllability of this net is 2. So, it is 3 plus 2 plus 1, it is 6. So, combinational controllability of 1 at this net is 6. So, this is how we can find out the combinational controllability of the full circuit by traversing from this level to this level. Now, you can easily analyze for some facts like, say for example, to test a stack at 0 fault here. So, to test a stack at 0 fault here, we have to apply a 1 over here. So, combinational controllability of applying a 1 here is 6, correct. And observing this line, because we are taking a stack at 0 fault, observation of this line does not matter, because it is same for both stack at 0 and stack at 1, because you can directly observe this. Now, you say stack at 1. So, to apply a stack at 1 fault, you apply a 0. So, in this case, you have to apply a value, the difficulty level is 3, because to take a stack at 1 fault, you apply a 0 over here. To take a stack at 1 fault, sorry, to test a stack at 0 fault here, you have to apply a 1. So, difficulty of applying a 1 is 6. Stack at 0, you have to apply a 0 here. Difficulty of applying a 0 is 3. So, stack at 1 fault testing is easy compared to testing a stack at 0 fault at this net. Okay, here we have for this net is directly primary output. So, the observability values are 0. So, we have not added them. So, this gives you some intuition. Similarly, if you consider this net. So, stack at 0 fault, you have to apply a 1, stack at 1 fault, you have to apply a 0. Difficulty of both of them are 2 2. So, they are equivalent to test over here, because observability is same for stack at 0 fault and stack at 1 fault at this net. But say for example, if I say that I want to compare what is the difficulty of testing a stack at 0 fault here and testing a stack at 0 fault here. Say that if I say that I want to test a stack at 1 fault here and a stack at 1 fault here. To do that, you have to apply a 0 over here. How difficult is to add a 0 over here? It is 2. Now, how difficult is to apply a 0 over at this net? It is again 2. But now, so you can say that testing a stack at 1 fault here and stack at 1 fault is easier, but that may not be the case. Why? Because you have to observe this line to determine a stack at 1 fault here, you have to observe this line to determine a stack at 1 fault here. Now, this line and this line are not same. As these lines are not same, so we have to also find out, also you have to add that how difficult is to observe this line, this combination observability of this one and combination observability of this one. So, whichever will be higher, that fault will be difficult to test. But now, for example, if you want to find out whether stack at 0 fault is easier to test at line or stack at 1 is easier to test at this line. So, if you want to compare the difficulty or easiness of stack at 0 and stack at 1 at a single net, okay, then observability may not matter much, because same line you are comparing the values. So, same line has to be observed. So, combination observability of this net is same for stack at 0 and stack at 1 both. Okay, but difficulty is only coming into matter. But if you want to compare 1 fault at this net and 1 fault at this net, so both controllability and observability will matter, because difficulty of observing this net and difficulty of observing this net may not be same. So, now we see for the same circuit, now how can we find out the combinational observability? That is, we have to do for this reverse propagation. So, now you see observability of this one is 0, primary output. Now, this is the level 1. Now, now we go to next level. So, next level, say you want to observe this net, say. This net we want to observe, say. So, how difficult is to observe this net? So, this net will be observed by this one. Okay. So, combinational observability of O1, that is 0, that 0 has to be added, right. Now, if you want to observe this line has to be a 1. So, how difficult is to make this line as 1? This is 2, correct, and then making this line as 1 as 2, and then we have to add a 1 for the level shift. So, observing this line difficulty is 3. Now, say we want to observe this net we want to observe. So, how difficult is to observe this net? So, difficult to observe this net is you have to make this net as 1, this difficulty is 3. So, 3 plus level shift is there, so plus 1, but this net you are observing through O1, O1 is a primary output. So, difficulty of observing O1 is 0. So, 3 plus 1 plus 0 is 4. So, difficulty to observe this net at the output is 4, correct. Now, this is about level 2 you have done. So, now we will go to level 4, level 3. So, say for example, you want to observe this net, you want to observe this net. Okay, so, observe this net is actually how difficult is to observe this net plus 1. So, 4 plus 1 is 5. So, this is 5. Now, you say that you want to observe this net. So, if you want to observe this net, you have to make this net to 1. So, how difficult it is? It is 1. Okay. Then you have to observe this net via this net. So, this has to be added. The difficulty to observe this net is 3. 3 plus 1. Okay. So, how difficult is to control? So, to observe this net, so you have to apply a, so to observe this net you have to apply a 1 over here. So, and how difficult is to apply a 1 over here is 1. So, we have added 1. How this has to be observed via this. So, this 3 is over here and 1 level jump. So, it is 3 plus 1 it is 2, 5. So, difficulty to observe this net is 5. This is how we can calculate. Similarly, if you want to say observe this net if you have to observe, so you have to make this net as 1. How difficult is to make this as 1 is 1. Then if you have to observe this net, it will be via this net. How difficult is to observe this net is 3. So, you have to add 3 plus 1 level jump 5. So, this net is 5. So, now if we have calculated for all excepting this net, this we have to calculate. So, we know that observability of this net is 5, observability of this net is 5. So, this fan out can be observed via this and this. So, minimum of them, difficulty of observing via this or via this is the observability of here, but here both of them are equal. So, we get the value of 5. So, had this been 4 for some reason, then we would have said that observing this line via this line is easier because it is 4 and this is 5. So, we could have written a 4. But now in this case both of them, both the what you can call this fan out and fan out are 5. So, this stem will also have a 5. So, now this completes our enumerating the whole circuit with controllability of 0, controllability 1 and observability. Now, you can easily find out which is the easier fault to test and which is the difficult fault to test. So, let us say that we test for a stuck at 1 fault here. So, to apply a stuck at 1 fault here, you have to apply a 0 over here. So, difficulty level is 2. And also you have to observe this at the output. So, how difficult is to observe this net at the output is 3. So, 2 plus 3 is 5. So, difficulty for testing a stuck at 1 fault here is a 5. Now, we say that we want to test a stuck at 1 fault at this net. To state a stuck at 1 fault at this net, you have to apply a 0, difficulty level is 2. Now, you have to observe this net at the output. So, difficulty to observe this net at the output is 4. So, 2 plus 4 is 6. So, you can say that stuck at 1 fault testing here is difficulty level is 5 and here difficulty level is 6. So, this may be a easier fault to test than this net stuck at 1. So, this net stuck at 1 fault difficulty is 5, this net stuck at 1 fault difficulty is 6. So, this may be a easier fault than this one. So, similarly, you can find out for in one go, you can find out the difficulty level of testing the faults by stuck at faults. You want to stuck at 0 fault, if you want to test, it will be combinational controllability of 1 plus observability, and the similar way for the if you want to go for a stuck at 1 other fault, stuck at 0 faults, it is combinational controllability of 1 plus observability. So, similarly, for all the faults you can find out in one scan of this circuit and one scan of this circuit. This will give you combinational controllability values, the reverse scan will give combinational observability values. For all cases, you find out what is the level of difficulty of the faults. Now, you can set up a threshold that whatever is lower than that threshold will be easier to test fault and whatever are difficult to test faults will be higher than the threshold. Now, based on this demarcation, you can easily find out which are the easy to test faults and difficult to test faults. Easier one you will apply random pattern and difficult one you can apply what you call this satisfy, propagate and justify approach. But it is a heuristic. So, there can be lot of inaccuracies and also the heuristic you have to set properly. If you take a very high threshold, then it may happen that you have a very less number of faults in difficult to test series, and then in random test patterns in the end you might land in problems. But if you have a very low threshold, then lot of faults will go to sensitize, propagate and justify approach, then the beautifulness or the easiness that is given to you by the random pattern generation will be lost. So, very carefully you have to set the threshold. Now, we go to the question answer section. In the question answer section we are saying that SQUAP is a heuristic which computes this controllability and observability in a very fast way. That means there will be lot of inaccuracies, there will be some inaccuracies. Can we? So, this method is inaccurate. So, can we give some example? Why is it inaccurate? Can you give some example? So, in this answer, yes, SQUAP is a what you called is an approximate algorithm. The main reason of its inaccuracies are it does not in SQUAP all the branches of a fan out are considered independent of each other. That is you can have say this is a fan out. So, this is one branch, this is one branch. Okay, so, there is some difficulty and all, but this difficulty level, this difficulty level, this difficulty and this difficulty level are correlated, because these two outputs are dependent on this input, because these are fan out input and these are the fan out branches. Similarly, you can say that in the same way you can say that this guy is dependent on this one, but because they all belong to a common transitive fan out point. But to make the things easier, SQUAP does not consider this. SQUAP considers that everything is independent and we solve the problem. This leads to inaccuracy. So, let us see why. Okay, so, let us see that combinational controllability of CCG1, let us find out. So, CC1 of G2, so that is CC1 of G2, that is how difficult is to make this line to 1. So, let us see. So, input this is 1 1 primary inputs, the fan out will be 1 1 over here. So, this is a level shift. So, it is 2 2 because inverter you just add 1. So, now in this case of AND gate, so how difficult is to get a 1 over here? It is 0 over here, it is 1 1, minimum of them plus 1. So, minimum of 1 plus 1, 1 comma 1 plus 1 is 2. How difficult is to get a 1 over here? It is difficulty to this one, difficulty to get a 1 over here and a 1 over the 1, which is 1 1 in this case. Okay, so 1 plus 1 plus 3 is there, and for the inverter this one is actually 1 1. So, it is just a level shift, so 2 2. So, now we have 2 2 over here. So, how difficult is to get a 1 0 over here? It is minimum of 2 and a 2 plus 1, that is 3, and again how difficult is to get a 1 over here? So, it is difficulty to get a 1 over at this one, this is 2. How difficult is to get a 1 at this net is 3 plus 1, it is 6. So, we get the value of control this net to control this net to 1, we have the value 6. But now we will see it is very interesting that you can never get a 1 over here. To get a 1 over here, it is saying that combinational controllability of this is 1 is 6, that is being said. That means you have to apply a 1 1 to get a 1, correct? Now to get a 1 and a 1 over here, you have to get a 1 and a 1 over here. To get a 1 over here is an inverter, so you have to get a 0 over here. So, to get a 0 over here, you have to get a 0 over here. So, this is 1 and this is a conflict. So, you can never get a 1 over here. So, difficulty to get a 1 over here is not 6, it is infinity. Okay, but SQUAP will say that it is having a finite level of difficulty, that is 6. That is not correct, because you can never get a 1 over here. So, stuck at 0 fault testing at this point is impossible. But still SQUAP will say that you can test it, the difficulty level is 6, observability is 0, so it is very good, at the level of 6 you can test it. But it should tell you in an accurate way that difficulty of getting a 1 over here is infinity, and that is why stuck at 0 fault cannot be tested, because of the contradiction I have said. But SQUAP will not be able to tell you this, because these two inputs, as I told you, this input and this input it considers as independent, but they are not independent, because these two inputs are dependent on this common transitive fan out point. This is dependent on this two. Okay? So, that it does not consider, and therefore, it leads to an inaccuracy. But it is a very fast algorithm, because in one forward scan and one reverse scan you can get out the values for everything, which is a very easy way to do, and it is a simpler algorithm, but sometimes still there may be inaccuracies, and we have to leave with the inaccuracies, because we want to get the answers fast. So, this brings us to the end of this module. So, in the next class we will go to another module where we will study in details about sensitize, propagate and justify approach, because in this lecture what we have covered in details random fault simulation algorithms, then we have seen an algorithm how to find out which is easier to test fault and which is difficult to test fault. So, this was all about random pattern generation. Now, once you have separated the easy faults and the difficult faults, so in the next series of lectures or the next module we will take up algorithms which is called D algorithm, PODEM, FAN and some other algorithms are there, which will solve in a formal way test pattern generation by sensitize, propagate and justify approach. So, that we will see in your next class. Thank you.